That really upsets me. All right, nothing I can do about it. Okay, so this drops down, and then plus 2/3 natural log x plus 1. We good?
Yeah.
Now the derivative. So what's the left side going to be? 1 over y prime, right? That's always going to happen. And the right side is really nice. Derivative of 1/2 natural log x, we just focus on that part. That's 1 over x, then times the half. So can I write this? 1 over 2x. Oh, and the next two are real easy, right? Derivative x squared, 2x. Derivative of negative x, -1, right? So I'm just taking derivative of each of those, power rule, and then just derivative of x is 1. Here, 2/3 comes along, times 1 over x plus 1, times 1. So that's it, right there. Is that okay? Multiply both sides by y. Let's do multiplication of both sides by y. And look, that's what y is up there, right? So y prime will be in parentheses 1 over 2x plus 2x minus 1 plus, if you want, you can put these two together. You could write 2 over 3x plus 3. If you want, you can distribute the 3 through to both terms. And then parentheses is closed, and now you come in with y on both sides. So, well, I came in with y on the left, now y on the right. Root x e to the x squared minus x times x plus 1 to the 2/3. There you go.
It doesn't matter if it's like in front or right.
No, it doesn't matter. You could put this whole thing right here instead. All right, so that's pretty helpful, huh? Yeah. All right, now we're gonna look at a different type of function. I mean, not different, just another problem, and let's just see what you think. Y is equal to x x to the 2x. There we go. If for some reason you need to go back and watch what I did, you can go into my other classes channel, and I did the logarithmic differentiation for them, and you can, because the audio is cut out, you know, if you really need it. All right. Anybody notice anything weird here? That's the first time I've ever put anything like that up on the board. The variable x is up in the exponent, and it's in the base. So look at, if I asked you to take the derivative right now of x to the 4th, everyone here would say 4x cubed, right? If I asked you to take derivative of 4 to the x, which is that flipped over, right? They switch places. It's 4 to the x natural log 4. That's what we learned last class. So this is x to a power. This is a to the x. So power function, exponential function, right? Those are that's the difference between these two. We have ways of dealing with each of these. That has the variable in both places. That is not an exponential function, and that is not a power function. So how do we deal with that, right? I mean, I wonder, does it even have a graph? Like, if it has a graph, it should have a derivative, right? All right, let's see if it has a graph. Bless you. X raised to the 2x. There it is. See it? It's like a weird J, right? It's kind of like a J. So there definitely are derivatives over here. So we should be able to talk about the derivative. But we can't deal with it. We can't use this method. We cannot do it because this requires that to be a number. 2x is not a number. Can't do it this way because this requires the base to be fixed. The base there is not fixed, right? Yes.
Could you like split it up to like x squared to the x?
But it would, yes, but it would still be x on the bottom, x on the top. Like it would not, you wouldn't eliminate the problem, which is the fact. No. That's a good try, but it wouldn't work. All right, so how about this? Just tell me if you agree with this. Is that right? And that's what we just did a second ago. And now I can drop the 2x out. I should probably put this a little closer. There we go, like that. Now I can use property of logs to drop the 2x out front. So my next line will be natural log y equals 2x times natural log x. Right? And now I can do the derivative. Implicit differentiation. So do you see this is logarithmic differentiation. It's the same thing we were just doing in the previous two problems. What's the derivative of the left side? 1 over y times y prime. On the right side, you have to take derivative. And to do that, you're going to need product rule. Here's your product right there. So the derivative of the first function times the second one. 2 ln x, good. Plus the derivative of natural log of x, which is 1 over x, times 2x. That's just going to be a 2, yeah. Is that all right, though?
Why did you go for the ln x before you went for the 2x?
Why did I go for the ln x? I did product rule. Derivative of this times this. Are you talking about that right there?
Oh,
Derivative of this is what?
2.
2 times this.
Oh, okay.
And then plus derivative of this, which is 1 over x, times this. That's this part. See it? That is a product rule right there.
But that would be implicit.
That is implicit because I take derivative of the left side also. That's what makes it implicit differentiation, is that you have to take derivative of both sides implicitly. And the derivative of this is chain rule, this right here. Yeah, I'm going to multiply by y on both sides. So it'll be the 2 natural log x that was there. These x's canceled, and that was just plus 2. And then I have the y that I'm multiplying right here. But what is y? X to the 2x. So the derivative of x to the 2x is that. Okay.
Important to factor out things.
I'm sorry?
Is it not important to factor things out like the 2?
I mean, important, it's not going to change our answer.
Is it any more simplified if you take out?
I wouldn't argue that it is. What's being suggested here is, could you pull that 2 out like that? I mean, yes, you can, but it's not, this is not any more correct than this is. Unless when you do that, something cancels and it makes it algebraically cleaner. It really is, it's the same thing. All right? That makes sense? That's really a really cool thing that we can do with logarithmic differentiation. We can take derivatives of functions of x that are very different than anything we've ever seen. We've got x's both in the base and the exponent. So if you ever are faced with a problem where you see x's down here and up there, and you're asked for the derivative, logarithmic differentiation is the way to go. And by the way, there is no other way to do it. Like, you don't have another way. Like the previous two problems I did, we could have done with quotient rule, right? And a triple product on the last one we did. We could have, and it would have taken a while, and it would have been ugly. This one, you don't have another option. Logarithmic differentiation is the way to do it. All right, y'all good? All right, you should be able to complete your homework now. You can go up and finish through all the, through 62? Yeah, I'm gonna let you do that. 3-5. And before I get to the 3-5, let me just remind you of some stuff from pre-cal, all right? So in pre-cal we had 6 trig functions, right? We had 6 trig functions in pre-cal. And what we've learned in this class is that every one of these functions we have a derivative for, right? We know derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared, derivative of cosecant is negative cosecant cotangent, derivative of secant is secant tangent, derivative of cotangent is negative cosecant squared, right? That's all on your formula sheet, right? Say that fast 10 times. But these weren't the only functions you studied in pre-cal. You studied their inverses also. So let's talk a little bit about the inverses before we actually get into it. What we did is we said, hey, look, if you look at the sine function, it looks like this, right? And it keeps going forever and it goes back this direction, same thing, right? We said, can we define an inverse function, a function that would undo the sine function? And what we realized is that in order to have inverses, and this would go back to college algebra, for a function to have an inverse, it first has to pass the vertical line test to be a function. And then to have an inverse, it must pass the horizontal line test, which means we can't hit it more than one time. And in this case, we do, right? So do you remember what we did in pre-cal to remedy that situation? We cut it, right? We said, okay, well, don't look at the whole sine function then. Let's just cut it right there and right here. And let's just ignore everything else like that, and just look at that little segment. In that little segment, it achieves its entire range. It goes from its lowest value to its highest value. So it goes from -1 all the way up to 1, right? And this right here would be the domain. The domain went from -π/2 to π/2. So if you take the sine curve, you restrict it between -π/2 and π/2, that piece is invertible, has an inverse. And we can define that inverse function to be this, or you might have seen, depending on your instructor, might have seen arc sine or this notation. They're the same thing. And how many of you saw this notation? Okay, this notation? Everyone else? Okay, that's the one I'm going to use, all right? This is perfectly fine, I just don't use it. And so what we said is for the arc sine function, it should undo that function. So let me give you an example. If I ask you right now, what is sine of π/4, you of course would tell me √2/2. √2/2. So you're looking at your unit circle, you're going to π/4, which is 45 degrees, and you're picking off which point? Sine is the y value. You're looking at that y value and you're saying √2/2. The arc sine function works backwards. So what it does is, let me just get rid of that for a second. If I say what's arc sine of √2/2, that takes you back to the angle that created that √2/2. So this would be what? π/4. Understand? I mean, I'm not here to teach you this. This you should have already been taught, but I'm reminding you of what it was, all right? All right, so, but we had to be a little careful with the arc sine, because if I give you something like this, arc sine of negative root 2 over 2, then you're saying where's your y coordinate negative root 2 over 2? So where does that happen? Where's the y value negative? Well, you can't be up here, right? Bottom? How about right there? That point right there is the point negative root 2 over 2, negative root 2 over 2. So there your y coordinate is negative, right? Negative root 2 over 2. That's not the only place. It also happens here, doesn't it? This is root 2 over 2 is the x coordinate, y coordinate is negative root 2 over 2. So which of these answers is it? Both? Can't be both or else it's not a function. It can't go to both places. That's the whole reason we cut it off. Because we have to only be able to, we need to all go back to the same answer. We can't have one person have it be one thing and another person have it be something else. No, that's general solutions of trig equations. No, that's not that. Look, this is 0 degrees, right? Pi over 2 is straight up. Negative pi over 2 is straight down. When we cut this thing between negative pi over 2 and pi over 2, that means automatically you're not allowed to look over here at all. Okay? You can't look over there. Because you're talking about an inverse sine function. You can't do it. That means it has to be this one. So what's that angle? You cannot go around and tell me what that angle is. Why? Because to go around means you have to be bigger than pi over 2. You're not allowed to. So you have to go backwards, negative angles. This is negative 45 degrees or negative pi over 4. So the answer to this is negative pi over 4. So there's more involved with these trig functions, these inverse trig functions. There's a lot going on. The first part of the homework set is like 7 or 8 questions of nothing but this. It has nothing to do with derivatives. It's just, do you remember from pre-cal how you evaluate inverse trig functions? So you'll be spending some time reviewing, I think. Now, what about cosine? Do we have the same, when we come up with the arc cosine function, do we have the same restrictions? Do we cut the cosine off at the same place? No, it's not. It's from 0 to pi.
So it's 1 and 3, right? 1 and 20.
Yes, no, it's 1 and 2.
1 and 2.
From 0 to pi. And then tangent, in order to define its inverse, we cut it off at negative pi over 2 and pi over 2. So you're going to need to go back and kind of review where these domains were cut to define these things. All of these had to be restricted. The most important ones are the first 3. All right? So, in pre-cal, you're introduced to 6 trig functions, and then you came to this class and I told you what the derivatives of each of those were. We proved the first one. I used the limit to prove it. I left that as an exercise, and then we proved tangent by using the quotient rule on sine and cosine. So all of the derivatives of these have been in some way shown. But now that we have the other 6 inverse trig functions, right? There's the arc sine, there's arc cosine. So for each of these, there's arc sine, arc cosine, arc tangent, arc secant, and arc cotangent. Or you could say inverse sine, inverse cosine, inverse tangent, inverse cosecant, inverse secant, inverse cotangent. That's 6 new functions. And you know what? We need to know what the derivatives of those are. And that's what today is about. They are on the formula sheet. All right? So, any questions on what I'm about to do? Like what I'm about to show you? It's not bad. So I want you to look at the rest of what I'm going to do here today in 2 parts. The first part is me proving the formulas that are on your formula sheets. I'm going to prove the first one, maybe 2 of them. After I prove those 2, then we're just going to use the formulas. You will not have to prove these, right? You will not have to prove them. Maybe as a bonus question on the test. But you need to see where they come from, all right? If I can show you where the derivative of an arc of a function comes from, I'm going to show it to you. So please get your formula sheets out and find your derivative formulas. These are them right here. those are them. They should be on the same page that the derivatives of sine and cosine and tangent are, right? Page 5. And here they are. They're provided for you there. What's interesting about the derivatives of the inverse trig functions is that, like, the derivative of sine of x was cosine of x, right? The derivative of cosine was negative sine. All the derivatives of the regular trig functions, sine, cosine, tangent, cotangent, all those, the answers were also trig functions. The derivatives of the inverse trig functions are not trig functions, right? They're just functions of x. And they all involve x squared, right? Don't they all have an x squared in them? They all have a 1 in there somewhere, right? So weird. Like, how are we going to prove that this formula is true? Well, I'm going to start with the very first one, all right? I'm going to prove right now that the derivative of arc sine of x is equal to 1 over the square root of 1 minus x squared. So I'm going to write it down first. This is what I'm going to be trying to find the derivative of. I want y prime, right? That's what I want. What's that?
Should we be writing?
Yeah, if you want to know how to prove these. Yeah, this proof, okay, although I'm not going to test you on it, part of what it takes to prove this is something that we use in Cal 2 a lot. And that's the reason I like to show it, because in Cal 2, you will use a certain technique in here, and I'll point it out when I get to it, that in Cal 2 you use a lot. So I could just give you the formulas and move on, but then later on Cal 2, where you're like, what are they doing? Like, you know, there will be a missing piece, and you're like, I never saw that. And I'm trying to show that to you, all right? All right, so here we go. I want the derivative of this, right? I can't just take the derivative on the left and the right because I don't know what the derivative of that is, right? You don't know what the derivative of arc sine is. That's the point. That's what you're trying to figure out. Right? I can't just write that down. That formula doesn't exist yet. So what I do instead is I take sine on both sides. Now the reason I do that is because when you put sine together with its inverse sine, the whole point of inverse functions is that they undo each other. Just like when you put e and natural log of x together, you got x. Or if you took natural log of e to the x, that was x. That's because these two are inverses. So when I compose these two together, take sine of sine inverse of x, they go away. The right side is just x. Agreed? All right, now the left side is just sine y. Any ideas on what I could do now? Differentiate. Yes, but how?
Natural log?
No, no. There's no powers. Implicitly. Implicit differentiation. Okay, because look, you're looking for y prime, right? Yeah. If I take derivative of sine of y, I'm going to get a y prime out because I have to do chain rule. It'll be dy dx, so I'll get that, right? So let's now take the derivative on both sides implicitly with respect to x. I'm going to box this, all right? That was the equation that I'm going to take derivative of. So the derivative of the left side is cosine y times dy dx, which I'm going to write as y prime. So I took derivative of sine of something is cosine of that something. Derivative of what's inside is right there. Done on the left side. Equals 1. Because the derivative of x with respect to x is 1. And now solve for y prime. Y prime equals 1 over cosine y. That's secant y. Isn't it? 1 over cosine is secant. So there, I've got it for you. You want a derivative of y, right? You want a y prime? I got it. It's secant y. But that doesn't match this answer. And the reason is because our answer for the derivative has y in it. And this answer has x. We need to somehow get this thing back to x. All right? I need to somehow get this back to x. With me? And the way I'm going to do it And this is what I was saying, I'm going to point it out when I get to it. This is the place where in Cal 2 you'll do this. I need to somehow get this. What is secant of y? And the only real information I have that connects y to x is what I boxed right there. You see that? I know sine of y is x. We need secant of y. So I'm going to draw over here. I'm going to draw what we refer to as a reference triangle. I'm going to draw a right triangle. There's a right triangle. Look at this equation right here. Sine of y is x. I'm going to rewrite the x as x over 1 because it is x over 1. And then I'm going to come in here and fill this triangle in. I'm going to use for my angle y. Because usually when you plug something into a sine function, isn't that usually the angle? Like sine of pi or sine of pi over 4. Sine of y means that this is an angle in this triangle. Could I fill out the rest of the triangle now? I'm saying that sine of that angle must be x over 1. What is sine? On a right triangle, what is sine by definition? Opposite over hypotenuse. Right? So I could fill out x as being my opposite side and my hypotenuse as being 1. Now why is that important? I mean, I'm looking for secant y, right? What is secant? How many of you all learned the SOHCAHTOA? Raise your hand. SOHCAHTOA? Where are my not SOHCAHTOA people? No, it's okay. You haven't? Should we tell her?
It's like the best thing to keep track of.
Okay. SOHCAHTOA is an Indian. She was a math genius. SOHCAHTOA.
No.
Yeah.
Yes.
Wait, what?
No,
But it just so happens that not only was she a math genius, her name, SOHCAHTOA, can be used to remember the trig functions. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA. Anyway, she was killed. It's a tragic story. We won't talk about it. Okay? So we want secant, right? Secant is the reciprocal of what? Cosine. Cosine is adjacent over hypotenuse, so this is actually needs to be hypotenuse over adjacent. On that triangle, if you can tell me what hypotenuse over adjacent is, you'd be done, wouldn't you? But you don't know this side yet. We can get this side pretty easily because it's a right triangle. We call this A for adjacent. Is that all right? We know the Pythagorean identity says that a squared plus b squared equals c squared. So I can say a squared plus x squared must equal 1 squared. And I can solve that for a. And when I solve that for a, I move. I just thought about this. I mean, I could probably get in trouble for saying SOHCAHTOA is an Indian name, right? I could probably get in trouble these days for saying something like that.
If you're trying to be politically correct.
Yeah, you know what I'm saying? It's pretty sad.
Yeah, we're not.
I'm not worried about anyone going and reporting it or anything. I'm just saying that's the day and age we live in, right?
Everyone saw, or most people.
All right. Are we good here? A is going to be the root of this. Right? I need to get the a squared out of there. So I take the root. I'm supposed to do plus or minus, but because a is the length of the side of a triangle, I'm only going to look at the positive. So a is this. And now when I say what was secant of y, like I said before, it'd be the hypotenuse over the adjacent, which is 1 over square root 1 minus x squared. There it is. Kind of, I guess, yeah. That's why I like to show this, because going from this information to here requires that you understand how to convert this into a triangle that can help you figure out everything else. Right? I mean, I could ask you now, what's tangent of y, right? What's tangent of y? This over this, right? All right. So that one is real important. You should on your notes, you should put a star next to this one, because that comes up a lot in Cal 2, that derivative. Remember I said Cal 2 is basically Cal 1 backwards? I mean, you do a lot of things backwards. You try and undo differentiation. It's called antiderivative. And so if you were trying to go backwards from this, you would have to know when you look at something like that, it comes from the arc sign. It is the derivative of arc sign, and that will happen a lot in Cal 2. The other one that's really important in Cal 2 is this one. This one is really important. All right, so let's actually prove that one also, because I think it's worth doing one more proof of it. So what would I start with here? What would I write down first? Y equals tangent inverse of x, right? I want to know what y prime is. You have no idea right now what derivative of arctan is. So you take tan on both sides, right? Tangent of the left side, tangent of the right side. You get tangent y equals x. I'm going to box that. That's what I'm going to use for my triangle in a little while. But now we can differentiate implicitly with respect to x. So what is the derivative of the left side? Secant squared y times y prime equals 1. Solve for y prime. Y prime, divide. 1 over secant squared x. It should be secant squared y. I don't know why I did that. And then I got to go to the triangle, but let me see here. Is this the same as? Oh, is that the same? Is this? Try it out. If you square 1, what do you get? 1. If you square a secant, you get secant squared, right? That's the same? What's 1 over secant? Cosine. Right. Cosine squared. This is really just cosine squared y. Y prime is cosine squared y. I need to know what cosine of y is then, right? If I know what cosine of y is, I'm in business. And then I'll just square that answer. So cosine is adjacent over hypotenuse. Okay, yes. So cosine is adjacent over hypotenuse, but we get our triangle from this. So I'm going to draw right triangle. What's the angle? What do I call that? That's y. And then tangent of y is a fraction, x over 1. Means my opposite side is x and my adjacent side is 1. Opposite, adjacent. But to do cosine, I need adjacent and hypotenuse. So I need to get the hypotenuse of that. I'll call it h. 1 squared plus x squared is h squared. And then take the square root on both sides. 1 squared is 1. 1 plus x squared is h. So to answer this question, right, y prime is equal to cosine of y. What's cosine of y? Adjacent over hypotenuse? So 1 over, what's the hypotenuse? Square root of 1 plus x squared. But that's cosine, but then squared. 1 over 1 plus x squared. Square the top, you get 1. Square the square root, you get 1 plus x squared. And that's the formula.
I have a question.
Yes?
Could you have avoided a few steps if you would have changed secant squared y to 1 plus tangent squared y, and then looked at your triangle?
Yes, you could have.
Solve for anything?
Yes, very